Yeah, Neha, will you share the screen? Yep. Hello, everyone. Welcome to our presentation on the Distributed Adaptive Resource Equalizer, or DARE, designed for the load balancing in modern systems. So, this project was developed for the CS 512 Advanced Operating Systems course. Let me introduce our team members. I am Akanksha Boga. I conceptualized and designed the DARE framework, focusing on hybrid architectures and resource management techniques. My teammate is Neha Devrapu, who developed the pseudocode for DARE, which focuses on adaptive load balancing and optimizing system communication. Geetanvita Ganji, who has conducted in depth research on the challenges and trade offs associated with DARE, particularly focusing on issues like communication overhead, decision delays, and energy use. And the next teammate is Rachna Dahagam, who has led the system architecture design specifically for the resource monitor and adaptive load balancer components. So let me start with the introduction. Modern distributed systems are becoming the backbone of industries like cloud computing, IoT, and mobile applications. So these systems consist of multiple nodes that are spread across different locations, working together to perform specified tasks. A major challenge, however, is ensuring that no node becomes overloaded while other remain idle, which can also lead to inefficient use of resources and degrade which and it also degrades the system performance. So our solution, which is DARE, aims to solve this problem by enabling adaptive load balancing in real time across distributed systems without relying on the central controller. Moving on to the next slide, problem and motivation. So, as systems grow, traditional methods of load balancing fail to keep up, especially when the system's conditions change rapidly. And there was also built to address this issue by, decentralizing the control, allowing each node to monitor its own workload and make decisions about how to balance the tasks which with nearby nodes based on real-time data. Moving on to the next slide, which is DARE framework. So DARE consists of two components. One is resource monitor and the second one is adaptive load balancer. Coming to the resource monitor, this module monitors critical resources metrics which like CPU usage, memory load, network latency, and battery levels. So each node here regularly shares its status with nearby nodes, it ensures the efficient communication by minimizing the overhead. Coming to the adaptive load balancer, if a node is overloaded, this component decides which nearby node should take over additional tasks, ensuring an even distribution of workloads. I'm next handing it over to my next teammate, Rachana.
Hello. This Now let's understand the diagram. This diagram illustrates the flow of operation in the distributed adaptive resource equalizer DARE system. A resource monitor. Each node in the system has a resource monitor. This monitor tracks the key matrix of the node, including CPU usage, memory load, network latency, and battery level. These metrics give an idea of how busy or ideal the node is. Monitor resources. The resource monitor sends the resource status to a component called monitor resources, which aggregates the processes the data from the resource monitor. Adaptive load balancer. Once the resource status is received, the adaptive load balancer uses the information to determine if the node is overloaded. Balance load. The balance load component determines which task should be offloaded from the overloaded node to another node with more available resources. Tasks. Finally, tasks are moved across nodes to ensure an even distribution of work, ensuring no node gets overwhelmed while others remain idle. Benefits of DARE. DARE provides a scalable, fault tolerant, and energy efficient solution by allowing each node to independently monitor and adjust workloads. eliminating the need for the central controller. Its decentralized designs ensure seamless task redistribution, maintaining performances even during node failures or system expansion. The system adapts dynamically to changing workloads and minimizes energy consumption with lightweight monitoring and communication, making it ideal for resource constrained environments.
Hello, my name is Neha. Let me continue with the pseudocode. Yeah. So, as you can see here, this code is responsible for resource monitor, which tracks CPU memory, latency, and battery. And then we have adaptive load balancer, which offloads task when a node is overloaded. So, I will explain you the code now. So, this is the code that I have written in Python. The code simulates a distributed adaptive resource equalizer system which aims to manage resources like CPU, battery, latency, and tasks across multiple nodes in a distributed system. It helps prevent overload by offloading tasks from overloaded nodes to underloaded nodes. So, this simulation runs for 10 rounds. So we have two classes here. One is node and the other one is their system class. This node represents a single computer or a device in the system. The node has attributes like CPU, battery, latency, and tasks. It also has methods to update its state and manage tasks. And the other one we have their system class. This is responsible for managing the entire system of nodes. It monitors nodes for overload conditions and balances the workload by redistributing tasks from overloaded nodes to underutilized nodes. And then main execution. So this block initializes the day system with 5 nodes and run for 10 rounds. Let me execute the code now. So this is the output that I got. So this runs for 10 rounds. And here, each node is an individual computer or device in the distributed system. We have 5 nodes here, and the percentage of the CPU the node is using. The higher value means the node is busy, and the battery level of the node, which decreases slightly in each round, and the tasks number of tasks assigned to the each node. More tasks means the node is busy. So in round one, we can see none of the nodes has taken the tasks. In round two, we can see node 1 and node 5 has taken the tasks. One, they are sharing the work here. And then in round 3, each and every node is sharing the work. So that's why we have one for each and every node. And in round 4 also we have one task for each and every node. And round 5, node 4 has two tasks because it is taking the work from other nodes. It is overdoing the work. So likewise, the work has been shared across all the nodes. As you can see in round 10, um, uh, all the tasks are, all the work has been shared equally among all the nodes. So the battery level of the nodes decreases with each round, which simulates resource consumption over time. As you can see, the battery level has been decreased if you compare nodes here. So, throughout the simulation, no node was overloaded, like CPU greater than 60. We don't have CPU greater than 60 in every round. So, the system balanced the tasks relatively evenly, ensuring that the CPU usage stayed below high thresholds. And the system attempted to ensure that nodes with fewer tasks on additional work, while nodes with more tasks balanced out as best they could. So, this is what the output. So let me hand over to the next person.
Hello everyone, I'm Gitanvita.
So, communication strategy. DARE optimizes communication by sending periodic updates only to nearby nodes, reducing network traffic. Tasks are redistributed only when thresholds are crossed, ensuring efficient resources use. Small, lightweight messages minimize communication overhead, and that is ideal for large distributed systems. Tasks are moved only when necessary, avoiding unnecessary redistribution. This will overall improve the system performance. And coming to the next slide, challenges here, the challenges are communication overhead, decision delay, local versus global awareness, and energy consumption and fault recovery complexity. There's decentralization approach can lead to an increased communication overhead, slowly system performance in large scale environments. Real time decision making may introduce delays, which will impact on time sensitive applications, and nodes limited local awareness can cause suboptimal decision, and continuous monitoring can increase energy consumption, especially in the resource constrained system. Additionally, fault recovery is more complex due to the independent failure detection and coordination among nodes. This will decrease the performance of the system. And conclusion, from overall all of this, we can conclude that DARE offers a scalable, fault-tolerant, and energy-efficient solution for load balancing, ensuring optimal resource use through real-time adaptive decisions. Its minimal communication strategy reduces the network traffic and energy consumption that makes perfect for large and resource reconstructed resource constrained systems like IoT and mobile networks. Thank you.
Thank you.